Hello everyone, this is Anli from University of Kentucky. I'm very happy to have the chance to give this 10 minutes talk, and I will tell you a story about an R-motivic V1 self-map. This is joint work with Prasid Bhattacharya and my advisor, Badong Giyu. So I'll start with a classical chromatic homotopy theory story that is the notion of type N spectra and the Vn self-maps. That SH denotes a classical stable homotopy category, and we grab a spectrum X and consider its rational homology. If that's non-zero, then we say X is of type 0. If it is 0, then we need to continue to consider the next level of more of a K theory, which is K of 1. So classically, it is the complex K theory Ku mod 2. If K1 of X is non-zero, then we say X is of type 1. If that is 0, then we move on and consider the next level of more of a K theory, namely K of 2. But for the purpose of this talk, we don't need to talk about that. So the connection between type N spectra and the Vn self-maps is the Hopkins-Smith periodicity theorem, and that tells us any type N spectrum admits a Vn self-map. So a great theorem, and let's look at the example in this talk. So let S mod 2 to be the cofiber of multiplication by 2 between sphere spectra, and S mod eta to be the cofiber of eta. And we can cook up this spectrum Y, that is S mod 2 smashed with S mod eta. So I'm gonna draw the cell diagram. So those two sticks are multiplication by 2, and the longer edges are eta. So this is the cell diagram for Y, and Y is of type 1, and by the theorem, it admits a V1 self-map V. So the special thing about this V is if we take the cofiber, then take the cohomology, we realize that to A1, which is the Steenrod subalgebra generated by square 1 and square 2. So enough classical story, and what about motivic? So first, let's consider the complex motivic. So we can cook this analog Y upper C using the same thing, just by replacing the classical sphere spectrum with the C-motivic sphere spectrum. And this Y upper C also admits a V1 self-map V upper C, and if we take the cohomology of the cofiber, we get the C-motivic Steenrod subalgebra A1 upper C. So almost not change from classical, but come to R-motivic, things are different. Why? Because, well, we have two R-motivic maps corresponding to the classical multiplication by 2. One is 2, and one is called H in modern works. That is 1 minus epsilon, where this epsilon is a twist. Yeah, we also have two ways to lift the classical map eta. One is the eta in the motivic thing that corresponding to H1, and one is you embed the classical eta into the motivic world, and that is called eta top in modern works. So we have many different ways to cook up our candidates for Y upper R, right? Okay. So what do I mean by this corresponding to classical maps or such? Then let's switch gear and talk about the connections between those stable homotopy categories. So here is my favorite square of stable homotopy categories. So this corner, the down right corner, is the classical stable homotopy category, and above that is the C-motivic stable homotopy category. To the left, that's the R-motivic one, and at the down left corner, that's the C2-equivariant stable homotopy category. So we also have connections, namely functors between them. Those vertical ones, those are the Betty realization functors. And down below here is phi upper E, so that's taking the fixed point with respect to the trivial group, also known as underlying functors or forgetful functors. So what's on top is the extending the scalar of varieties. If you try to think about the stable homotopy motivic category building using varieties. So there's also the geometric fixed point functor phi upper C2 from SHC2 to the classical stable homotopy category. So that is to say, if we have something here in the classical stable homotopy category, we can consider to pull it back along phi upper E and phi upper C2, so things will land in this equivariant stable homotopy category, and then we can continue pull it back along Betti realization, so that will result in the target landing in SHR. That is the place we're trying to define things. Okay, so this is the motivation for this notion of type n, k spectra and the V n, k self-maps in SHR. So let's grab an R-motivic spectrum X, and we say X is of type n, k if the underlying of X is type n and the geometric fixed point of X is type k. And given such a spectrum X, we can consider a self-map F between that. And then we also define things by sending things to classical and define there, or I can say by pulling it back. So if the underlying of F is a Vn self-map together with the geometric fixed point of F is a Vk self-map, then we say F is a Vn, k self-map. So here, n and k can be nilpotent. If you send it to classical, that's a nilpotent map. So now let's come back and talk about our Y upper R. So the candidate we use is S mod H smashed with S mod eta. So this Y upper R is of type 1, 1 because the underlying is the classical Y, which is of type 1. And the geometric fixed point of that is 2 sticks. So each one is multiplication by 2. And because the geometric fixed point of eta is classical 2, and the geometric fixed point of H is trivial. So our theorem is this Y upper R admits a V1 common nil self-map, and the cofiber of that map, if you take the cohomology of that, is gonna be the R-motivic Steenrod subalgebra A1R. All right, so this gives one realization of A1R. But there are many more. So we discovered that there are 128 extensions of A1R to an AR module. Wow, right? So now we are trying to figure out in our current work whether they can all be realized by some spectrum. So if you feel like this story is interesting, please drop by my session on Thursday, October 22nd, or email me. So here's my email address, and thank you very much for listening.